Hello, I'm first year. My name's Henry. I'm very interested in machine learning. Thank you very much to everyone organising this to let me give a talk on it. So here goes. So I'm sure you've all heard of it quite a bit. Does anyone want to help me out? What is machine learning? Yeah?
It's what machines learn.
Okay. Okay. I suppose in a way, yeah, it is quite analogous to learning. So machine learning is really useful for things that are really difficult to explicitly tell computers how to do. It's got a lot of drawbacks, but if you had to write an algorithm to say that this image is a dog or a cat, that would be really difficult. And actually, if you just have a load of data, and we live in an era where lots of data is being collected, it's the era of big data, then this is something you can achieve in machine learning. And it has drawbacks, but where there aren't other options, it's really useful. So these are some of the kind of tasks you can do with it. You can do like classification, so in this case of images, do classification of numbers. We're going to try and demonstrate that. This is a lot simpler task, obviously. You can also do classification of more complicated data, like, for example, natural language, like an email. Is it spam? Is it not spam? But you could use it for other things, like there are subdomains within machine learning about things like reinforcement learning for playing games like chess. And actually a surprising amount of problems in the real world can be modeled as a game, because a game is just a kind of abstraction. It's a predefined set of rules and objective. And actually, if we can train AI to be very good at games, that's very useful for us if we want to make self-driving cars and things. I should say, I'm considering machine learning a certain kind of AI. AI is like a broader superset that might include other things like tree searches and that. And it's hard to define. So I'm not necessarily, my interests aren't solely anchored in like this, but they are majoritively in this, and I don't have all that much knowledge about cybersecurity, but there are concerns with machine learning that make it important that we understand how it works. So machine learning is all about the data, garbage in, garbage out. And actually, if we can't secure the data and secure the model, if we put more and more systems in the control of machine learning, that could bode very badly, because if you can manipulate the training data, you could, for example, get a self-driving car to crash when it receives a certain input. Or if you can actually interrogate a model in a certain way, you might be able to learn how it works inside and then produce certain inputs to manipulate what the output should be. So there are unique problems with it. So it's important to understand how it works. So in terms of understanding it, the very simplest example, arguably, would be like linear regression, because a lot of machine learning is just essentially curve fitting. So in this case, the problem is, can you find a function that goes through a certain number of points and meets them as a line of best fit? Like, what's the best line you can find? So in this case, what we're trying to do is basically create a model which takes as input the x-coordinate, produces as output the y-coordinate, and it has these parameters which we're trying to learn. So in this case, 2 parameters for y equals ax plus b. This would obviously scale to a much more complicated system, like a neural network with many inputs, many outputs, many parameters. But to get the simple idea of it, now what you could try is you could create your model. You could come up with some initial guess for what the parameters should be, and then you could see what it outputs and then score it. So you could say, how well is it doing? How well is it learning the y coordinates? We're going to try and minimize this score, which is the loss. And then to do this, we're just going to try slightly changing the parameters. We're going to try and slightly increase or decrease each of the parameters and go with the ones with less loss. But this might be quite tricky because you might not do a small enough change. It might not be very numerically stable. So one of the things maths gives us to deal with this is differentiation. So if we have a differentiable set of functions, we can actually tell how we should be changing the parameters in order to minimize the loss. So we can phrase this as an optimization problem, and then we can actually solve it approximately. So to be specific, in this case, if our current model was a line, in this case parameterized by A and B, we're trying to figure out what A and B should be to best fit the data, where we have a whole bunch of data points, and for each data point we're trying to minimize the distance between the data point and the line. Or in some cases, like here, we might try and minimize the distance squared. So we can do this with calculus, which tells us how we should basically change the parameters. And based on the gradients, we can adjust the parameters. And I'll have a demo of this a bit later. And with this information about the gradients, we can use an algorithm called stochastic gradient descent. And what that essentially allows us to do is repeatedly improve our estimate for what the parameter should be, so that we can get to the very lowest loss, so we can get to the best possible approximation of the function we're trying to learn. So for any given pattern, if we choose some parameterized model which is very general, so some set of parameters will probably do the trick, this will let us learn those set of parameters. And so essentially, the gradient tells us the direction of steepest ascent, so we want to act in the opposite way to reduce the loss. And it gets slightly tricky because we don't want to get stuck in like local minimas and things. We want to try and get the true lowest loss possible. So people come up with all these clever mechanisms like momentum. We also don't want to just spiral out to nowhere, so we need to try and make our step size reasonable, so we don't have this kind of situation. And so what you do is you'd use a formula like this, which you essentially will improve your estimates by using the gradient multiplied by some value that just is like the step size, in this case the learning rate. And this is actually surprisingly generalizable. So with this, if we have another kind of problem, like if we need to fit a more complex curves, in this case our function is a polynomial with more parameters, but it's still differentiable, we can use the exact same approach and we can fit the curve in the same way. So a question for you, to try to demonstrate another concept. Which of these curves, the blue or the green, do you think better fits the red data points? You know the answer, so someone else.
I want to make a guess.
Can I answer the person behind Sal on the right? Sorry, Sal. Yes. So in this case, you can see that the green curve actually goes through all the data points. So by our metric, it should have exactly learned the data. But the blue learns the more general pattern. So if we added in some extra data points, which are maybe the ones we encounter in real life, you can see that actually the blue curve was a lot closer to those ones. And so for unseen points that it wasn't trained on, this green curve has essentially memorized the data, and so it performs really poorly. And so this is the idea of overfitting. So when you're training your models, you have to be careful to not use an overly complicated model, because then it might memorize the data and actually not learn generalizations about the pattern. So in principle, you should try and use the simplest possible model you can to solve the problem, which is part of the issue at the moment, because everyone jumps on the hype wagon. People are trying to use transformers for everything. It's a terrible idea, but they are really cool. So you might break up your data. I've written here the 70-20-10 rule. You might break up your data into some for training, some for testing, and some for validation. Now, if we got into a slightly more complicated, function you're trying to learn, you might have functions with more than one input. So in this case, we're trying to learn some kind of function from a bunch of data we have, which takes in certain parameters, about, for example, a student and produces the probability of them passing a test from 0 to 1. And you can imagine, if you weren't really sure how to go about this and you just wanted to try a few things, and say these are all like numerical values, you might try weighting each of the inputs to your model, IQ, hours studied, day of the week, by their importance. Maybe if it's Friday, students do worse, but overall it's not that important, and actually maybe the hours studied is very important. And so you might come up with some kind of model like this, where you try and learn essentially these weights, the relevant importance of each of the inputs, and then just take the sum. Can anyone see a problem with this if we try to use this model to give us the probability of passing a test? Go ahead.
It appears to not be bounded at 0 or 1.
That's right. So in this case, we want to kind of strictly enforce probabilities have to be between 0 and 1. So we might be able to use a function, in this case, sigmoid function or logistic function, to bound it. So literally just take whatever the value is, put it between 0 and 1. And we might also want to add on this little term b, because all the weighted inputs kind of say how much the student has going for them to pass the test. But it might just be a very hard test. So we might want a significant negative factor applied to that, so we might want some other factor. And if you come up with this model, you've essentially discovered a neuron, because this is the underlying function within a lot of neural networks. So you might have seen diagrams like these. So this represents a neural network. Each of the little circles is a neuron, and for the neurons after the input layer, what they essentially do is they take in as inputs the activations of the previous neurons in the previous layer. They take a weighted sum of them, they apply a certain function, and then they return that value, and the next neurons use it. It was inspired a bit by the brain, the idea that neurons that fire together wire together, but it doesn't really work in the same way. But this is a really useful structure because it can learn a very large array of patterns, and you've essentially learned a universal function approximator if you combine a bunch of these neurons together. This idea of having like many hidden layers, this is the concept of like deep learning, if you have lots of layers in your neural network. So, for instance, you can solve the problem of categorizing numbers. So this is a well-known data set in machine learning, the MNIST data set. It's like kind of like the hello world of machine learning for starting out. You can categorize handwritten digits really quite easily with a neural network. And so in this case, you would essentially apply the same principle. You'd have some kind of cost function that scores it based on what its output was, what the expected output was. And then using differentiation, you can basically change all of the parameters iteratively to train the model on a certain amount of data to learn the correct parameters. And so this is the cornerstone. This kind of model, like a simple one like this, you might hear being called a perceptron, because it doesn't have any quirky features like convolutional layers or anything. But really important. So I do have, and I'll share it after the talk as well. Oh, sorry, my computer's crashing. I do have a notebook demonstrating some of these ideas. Oh dear, this is quite unfortunate. Sorry about that. Well, I was trying to show you a notebook that... Oh.
Good.
It's...
it's E4PC.
It just kind of went unresponsive.
That's good.
Yeah.
Good.
Yeah.
Brilliant.
Yeah,
Okay.
excellent. Sorry. Okay, I'm going to try and restart this, but I'm going to move on to a different part I wanted to talk about, which is the transformer. So this is more of the rage nowadays. Has anyone heard of a transformer? Now, put your hand down if you think it's an electrical appliance or it fights Decepticons. Okay, well, so transformers, they are essentially the T in GPT. So GPT stands for Generative Pre-trained Transformer. And what they are being used for now is processing sequential data. So they're basically a deep learning architecture, and they were discovered, or invented, I suppose, by a paper called Attention is All You Need, which came out in 2016, 2017. Oh, I think let's come back. And you see them being used at the moment for like chatbots and things, because they are really good at natural language processing, but they can be used for other things as well. Hey. Excellent. I'll get back to the practical demo. So, can anyone tell me what these forms of data might have in common? I've tried to show stock prices, audio, text. There's probably a lot of right answers to this. But what do you think, Isaac?
It's like a list, there's multiple entries.
Yeah, exactly. So it's kind of sequential data. So maybe it's sequential over time, or you say maybe with text is like a list, but there's kind of an order to it. And there's a lot of data naturally organized like this, but you can also organize other data like this. So you could take an image and you could chop it up into a whole load of tiles and have it as a sequence of little smaller tiles. And the way that people used to process this data up until transformers was they'd use something called recurrent neural networks. So these are essentially an architecture where you have a neural network where the neurons take their last input as input again after you pass in multiple values. So you'd pass in, for example here, the value for the quick brown fox, and you'd pass in a sequence of data, and it has a kind of internal state in memory, and then you would get the output, ideally, potentially a dog, to complete the sentence. But these had a lot of problems. In particular, they're inherently sequential, so you have to pass in the data sequentially. It's harder to parallelize. And they also didn't deal with long distance dependencies. So if you have a sequence of text and you have some reference to something that happened quite a few sentences ago, this kind of model would really struggle to learn it. So that's where we get into transformers. So this is a diagram you might see. I think it's kind of horrible if you don't know what it means. It's very intimidating, so I'm going to try and avoid using that. But I'm going to try and explain, in principle, how something like GPT-3 works without going to the maths. And then I'm going to try and give a bit of a demo of something else that's a bit simpler using transformers. So ChatGPT is like a service. We use it. It acts as a helpful chatbot, but GPT-3 is a transformer model. And it takes in text as a sequence and basically produces new items in the sequence to produce more text. And the way it actually acts is as an incredibly sophisticated text prediction model, which, as they trained it on vast amounts of the internet, happened to also learn many languages and basic maths and lots of other strange, odd things, which is why it feels a bit like AGI, just this tiny amount. But if you, when you actually interact with it, you'll give it some text, and this text will be chopped up into little parts. So I've tried to represent that here. So these parts are called tokens. They could be words, or they could be parts of words. So you might have practice and ing, or walk and ed for walked. And And generally, neural networks, they process numbers. So words are kind of discrete and complicated, and we associate certain semantic meanings to them that would be kind of hard to imagine how you'd encode that so a machine can understand that. So what you use, there are dedicated models, and they're very interesting in their own right, which basically convert words, parts of words, or these tokens, into vectors. And so you'll chop up the text that's given into an array of tokens. You'll convert the tokens into vectors. So something like GPT-3 will use vectors of about the size, I think, 1,200 items. So they're relatively large, and each of the kind of dimensions of this vector represent a kind of semantic meaning. So you can imagine, for example, if you have the vector for queen and then the vector for maid, they might be similar in one dimension that represents kind of the feminine aspect, but then maybe very different in another dimension that represents like class or something. And so you can do kind of essentially arithmetic with these tokens. So you might be able to do, for example, king minus man plus woman, and then the result would be a vector similar to queen. So there are surprisingly kind of useful encoding of what these words mean. And so once you break up the sentence into basically an array of vectors, you're going to put it through the transformer. And a transformer, essentially, GPT-3 uses a sequence of what's called attention blocks, in this case self-attention, and then neural networks, which are like the perceptrons we saw before. And attention blocks were really the new thing this paper came up with. Attention is all you need. It was this idea, you don't need recurrence, you don't need these other things. If you have dependencies where one word affects another, the attention mechanism can handle it. So without the maths, if I were to try and explain it, the attention mechanism essentially allows words in a sentence to kind of exchange meaning and talk to each other in a way that lets them enrich their meaning to be more contextual to the sentence. So, for example, when this sentence, broken into tokens, goes through one of the attention blocks in GPT-3, the word car could, for example, you can imagine it kind of calling out and going, hey, are there any adjectives around? And then you can imagine the word expensive and the word red going, yeah, we're adjectives. And then essentially the meaning of car, this little vector, is adjusted to encompass some of the meaning of the idea of being expensive in red. So I've tried to represent, this is from Dali, like a generic car, and as it goes through the mechanism, it takes on some of the meaning of the other words to become more in context. So now the token that was before a generic car represents now a red car that's expensive, and maybe it was in the past tense. And so essentially, you're going to have this sequence of tokens processed in parallel, which lets you make these massive models quite efficiently through a bunch of these blocks, and then neural networks. And each of these blocks will adjust the meaning of the tokens to kind of enrich the meaning so that they are more in context, more kind of understood. I'm trying to avoid anthropomorphizing these too much. And so self-attention will look at the kind of context of the tokens, relation to each other, and then the neural networks will look at the semantic meaning of the tokens. So, for example, if you had a sentence like, the dermatologist was very suspicious of that mole, the word mole, when it's converted to a vector, could represent the aggregate of all possible meanings of the word. It could represent a spy in an organization, a number of atoms in chemistry, a mammal. And then it goes through this block, and the self-attention mechanism sees actually it's related to it's related to kind of the idea of a skin condition. So actually we're going to adjust this vector to represent the idea it's more specifically a mole, it's a skin condition. And then the idea of the neural networks is they'll add more of this semantic meaning. So they'll see it's a skin condition a dermatologist is suspicious of as being ideas encoded in this vector mole. and they'll add the ideas potentially anxiety. What if it's melanoma? And so if you have enough of these blocks with enough parameters, the thing that's amazing about these models is they can act in a very human way. Like, people originally thought transformers would be used just for machine translation, but they're incredibly powerful, which is very surprising and impressive. So I've tried to just chop out part of the diagram here. If you looked at the architecture of GPT-3, this would essentially be it. So what you have, you're going to take in your text, chop it up into tokens, encode the tokens as vectors, and then these vectors get passed through lots of these self-attention blocks and these neural networks repeatedly so that they can talk to each other, essentially, pass on contextual meaning, and then become quite enriched so that at the end, the sentence, the dermatologist is becoming increasingly suspicious of that mole, each of the words has kind of accumulated the meaning of the others. So the final token mole might now represent an object that a specialist is suspicious of, which is quite a difficult thing for us to imagine. And then the way that GPT-3 works, it's what's called an autoregressive model. So the final token is essentially used to create a probability distribution of what the next token could be. So from the word mole, which has been enriched to encompass all the ideas of the sentence, you can say, right, what's the probability the next token is a full stop, or the word he, or something else. And you create this distribution, you then sample from it, so you just pick something at random based on the probabilities, and then you input the whole sequence in again. And if it exceeds the length of your context window, the maximum size of sequence the transformer can process, it's going to knock off the oldest token, put in your new one, and put it through again. It goes through the self-attention again, you get a new probability distribution, you sample from it, and it goes in again, which is why these models you can write regenerate output, and it gets a different output. They're not deterministic in that sense. And so it is essentially like really clever predictive text. To try and demonstrate the principle of self-attention in a much easier way, because these models are massive and very hard to train. There's a model called BERT. Has anyone ever heard of BERT? So BERT stands for Bidirectional Encoder Representation for Transformers. All bidirectional means is that words can talk to words on the left and right of themselves. Whereas the way GPT works, words can only absorb meaning from words before them. And this made it easy for the model to be trained in parallel on massive chunks of the internet. Because you would just input a huge text corpus, and then for every word, say, what's the probability of the next word? Well, you know the next word, and you can say, all right, you were wrong, I'm going to improve the model from that. So, whereas GPT-3, look at the diagram, is just the right part, of this big diagram here, BERT is just the left part. So you've got the encoder and the decoder. Don't need to worry about all the little details, but essentially, BERT isn't going to be creating new tokens. All it's going to be doing is trying to understand a sequence of text. So use this self-attention mechanism to interpret the context and the semantic meaning of the tokens, and then essentially produce something we can use to classify the text. So if I go, so I'll try and do a practical demo. Does anyone have any questions at the moment? I'm sure there are loads, but feel free to fire them out. Yeah, that's fine. Feel free to just interject with them. I'll make sure to attach this resource as well. But this was a notebook I encountered which was incredibly useful at helping guide you through what BERT does if you're interested in learning more about transformers. And essentially, so I didn't make it, to be clear, hence why it's actually got good visuals. And essentially what we're using the model to do here is process movie reviews, which are small bits of text, and just categorize them as whether they're positive or negative. So in this case, visually stunning is probably positive. I think, if it says the dregs of the cutting room floor, it's probably negative, but that's quite hard for a computer to learn. So in this case, all we're doing is we're taking that model BERT, which just produces, understands the sequence and produces this little token called the CLS token for classification. And then we're adding on a little model at the end called the logistic regression model, which is what we did here. This is just a logistic regression model where you just produce a probability through a linear sum. And surprisingly, I think it's quite amazing where technology is at the moment, you can actually create your own model to categorize movie reviews. And so in this case, without using any kind of special techniques or fine-tuning, as you might call it, you can actually get about 80% accuracy, which I find really quite impressive. So in this case, we're just training that little linear regression model at the end. We're not training BERT. That's already come trained. And we just add something on at the end, and then we can categorize movie reviews. I also have a notebook, which I was hoping to show for the slight technical issues, which just represents some of the ideas that we looked at earlier. So the idea of kind of like curve fitting. So if you have this kind of problem, how would you go about learning the curve that best fits the data? And then it actually has all the maths here explained, but you can, as we said, apply the principles and you can learn a curve that is a much better fit of the data. It's also got an example here. If anyone wants to get into machine learning, TensorFlow is a really useful library. It can do it mostly all for you, but you will need some knowledge to debug it. Go ahead.
Why would you recommend inferior library?
The inferior library.
They don't change everything every update. Like Google.
So I think if the most kind of commercial libraries to probably know for machine learning would be scikit-learn, which I think the previous example used a bit, PyTorch and TensorFlow. But yeah, I'm sure they have their individual frustrations. But yeah, that's assuming you want to do it in Python, which has probably got the best support for it. So in this case, just the example with handwritten digits, you can actually just create a small neural network here, which just represents a neural network with 2 hidden layers with 20 neurons in the middle. And you can see it's really simple. You just call methods to train it. All the maths is done for you, and you can get about 95% accuracy, which you can improve significantly. But yeah, thank you very much for listening. I hope there are some questions, but if not, that's fine.
I'll ask.
Sure.
Why didn't you use mixed groups? That's it.
What's that?
It's the best machine learning algorithm. It's 100% interpretable. It's better decision trees. Why didn't you use it? I use it for everything.
So this raises a good point. So one of the machine learning has a lot of problems. So in a way, it's kind of terrible. Like, you would only use it if you couldn't write an algorithm to do it. So if you want to write a program to play tic-tac-toe, don't use machine learning. Do a tree search or something. And one of the big problems is interpretability, because these models, they act like a black box. You can't look inside them and really see how they've gone about doing what they're doing, like what they're thinking. The attention mechanism is actually quite beneficial in that sense because it is more interpretable. But for that reason, you might not always opt for machine learning. You might opt for other.
XGBoost is the best because it's 100%.
Yeah.
Why would I use it for?
Well, some things like transformers show that machine learning can still be useful for some tasks, even if you want to use one thing for everything. Generally, it's good to have a diversity of use cases. Yeah, Isaac.
So with the tokenization, so there was in there was one word that was split up into multiple.
Yeah.
But there was also, well, how do you tell where the spaces are if like play is like two listed trees and then play S are also two listed trees? How do you tell if it's like? How can you tell if or upcoming? How do you know if up is a word or joins to?
So.
Or is that just an example?
So this was just an example. I created it to illustrate the concept. The way these things work, there are individual models which are dedicated to encoding, like breaking up tokens and encoding them. That's not new to transformers. That was a technique in NLP for a while. I should say NLP being natural language processing. But in a transformer, you would learn the kind of encoding and decoding as part of training the whole transformer. In this case, the way that most of these kind of token schemes work is that they don't represent words exactly. They represent words and parts of words. So I tried to illustrate that by breaking up words like practice, sing into practice and ing. But yeah, there are various algorithms for it, but you might imagine chopping up by space and then chopping up some big words into smaller words. So I think GPT-3 might have about 50,000 tokens. Don't quote me on that. But yeah, so they won't have every possible word. If you have some crazy name of some kind of supervillain in some card game, it will have to break that up individual characters. So it won't have it. But yeah, that's the idea. Go ahead, Max.
I heard from some people that there's apparently LLMs that improve your privacy by obscuring the data. How practical do you think that is?
So when you say obscuring the data, whose data are they obscuring?
The users, I think.
So I'm not entirely sure I follow what.
I'm not too sure either, but it's on third-year projects.
You can try XGBoost. Advertising.
Sorry, I have to. You could ask me at the end. I have to go back to you. I'm not an expert in this at all. But sorry, do you have a question?
Maybe try to comment on that first. So there's this kind of technique, I suppose, in machine learning called federated learning.
Okay.
And so the idea is it's meant to be kind of privacy preserving. So the idea is that so if you let's imagine kind of privacy preserving can improve the performance of models. So the idea is you don't sort of share the data that you're using for training. You share the model parameters, maybe like a central, so you do like local training.
Okay.
For example, on my mobile phone, if I want to train on my personal data, I share the model parameters with a central, they do some sort of aggregation of that.
Okay.
And then redistribute model parameters that could be what we refer to. And this was a really, really hot topic at the moment. Research around trying to do that for LLMs, surprisingly.
Yep.
About LLMs at the moment.
Yeah, that would make sense because I imagine it would be difficult to get the data you inputted and got as output from those parameters, provided you could aggregate them. That's interesting. I'll look into that. Yes.
Looking at your consensus analysis, how good are you picking up things like human insert things like that?
So that's a really good question. So I joined a group in Lancaster called the NLP group, and some of the PhD work that I've seen is looking at how these LLMs, how can we make them learn things like idioms? So that is something that's actively being looked into. I'm partly kind of challenged by the fact that if you have, so this would be like something that involves collaboration with linguists, and in some cases I think I've been where there's a bit of disagreement. For example, if you're trying to identify a metaphor, sometimes people don't always agree on what's a metaphor, which makes it a bit tricky. But for sure, sarcasm is an important way of how we communicate. The hope would be that that kind of neural network would identify it. I think as well, perhaps there's a role to play in the models that can process audio data as well, like the latest kind of GPT-4o and things like this that process not just text data. Because if you see like a friend WhatsApps you and they say something sarcastic, it might be harder. So we might be giving it a harder task in that respect. But I think that's something that's being actively looked into, because I think there are improvements to be made in that aspect. No worries. Yeah, cool. Thank you very much for listening.